Hello and welcome to SDC 2023. And today's topic here is aptly called Trucks Keep Right. And what we want to talk to you guys about is an exciting new fiber channel technology that we call as virtual lanes, and how virtual lanes can improve efficiency and provide quality of service and potentially kind of relieve congestion in fiber channel SANs and a bunch of different use cases. My name is Nishant Lodha, and I'm a technical marketing engineer for Marvell, working in the storage group. And along with me is...
Hello everyone, this is Girish Basrur. I'm part of the Fiber Channel engineering group in the storage team at Marvell.
Thank you, Girish. So we will be our two hosts today, Nishant and Girish, and we'll be keeping trucks to the right. Okay. So I just wanted to jump in, and in case you were born within the last, 10 minutes, or maybe last couple of years, you probably have heard about what fiber channel is. But just in case, a fiber channel is a storage fabric, which is a fabric which is very popularly used in enterprise data centers for tier 1 applications when they need to access external storage, reliable, secure block storage connectivity. Applications, there's a bunch of different applications that rely on fiber channel. You start from a lot of banking and technology sectors, the cloud, healthcare. Basically, whenever your applications need secure, reliable, high performance access to storage, fiber channel comes into play. And as you see, typically there is a server within PCIe card, which is a fiber channel HPA that connects to a switch and then connects to the storage that this server needs access to. The point that I want to make here, along with this introduction to what fiber channel is that fiber channel as a protocol works on a credit-based mechanism. And what I mean by a credit-based mechanism is that two devices directly connected to each other on a fiber channel SANs tell each other how many credits they individually have, or give credits to each other. And that credits basically determine how many frames or packets can be sent to them without they requiring an acknowledgement. Think of that as the amount of queue and amount of space they have before they cannot accept any more packets before they have processed them. So it is similar like in credit card. You can't spend after you run out of your credit limit, and your credit limit is told to you by whomsoever provides you that credit. And the foundation of the technology that we want to talk to you guys about, which is virtual lanes, is basically based on this credit-based mechanism, and actually extends the credit-based mechanism to some things more interesting. And that technology is called virtual lanes, or VLs. And what we want to do is briefly tell you about what this technology is, or what are VLs, and what are some of the different use cases that me and Girish have been discussing internally at Marvell with a bunch of different partners and customers. And our combined kind of reason why we are here and talking to you about virtual lanes is certainly to introduce the technology, get you excited about it, but also ask you to consider the use cases that we are talking about if they seem interesting to you. If they seem something that your customers, your applications, your storage or server infrastructure could utilize to solve a problem, come talk to us. Think of this, talking about technology and use cases like spaghetti on the wall, and you tell us what sticks and what is interesting for you. Okay, so let's do a quick, before we talk about how virtual lanes work and how virtual lanes came about, so to speak. Let's talk about how a traditional fiber channel SAN works. What you see in this picture is that you see two servers on the left-hand side, server 1 and server 2. They both have a fiber channel HPA in them. They are marked as FC, and they are connected typically using a single lane to a top-of-rack switch, which then can have multiple different lanes that connect to a director class switch, which then takes the destination, which is the storage itself. In this case, storage 1 and storage 2. Where I want you to kind of look at is the different colored packets that are flowing between the fiber channel HPA and the top of the rack switch, because this is a single lane, which means that any frames that are ahead of you can, if they are slow moving, can cause head of line blocking. And because end of the day, it's a single lane. Imagine being on a single lane on your inside streets and having a truck ahead of you. What happens? All the traffic slows down. So if this server and this HPA, there was a flow that was talking to a relatively slower storage. Everything else gets choked behind it. Now, that is a problem, right? Now, since we talked about the credits mechanism earlier, the way the credits work is the way the acknowledgement for relieving these credits is a concept in Fibre Channel called RReady. And what has happened is this concept in Fibre Channel called RReady, which basically applies to a physical lane, has been extended to call either ER ready or VC ready. And I don't want to go into kind of what they mean or what they are, but one of them applies to one switch vendor, another one applies to another switch vendor. They are implementation specific that you don't need to worry about. The point is that what virtual lanes is that you see the same picture here now at the bottom, and you see that between the HPA and the top of rack switch, now there are multiple lanes, and currently we have 3 lanes available. And these 3 lanes can have different priorities or can have different priorities. And then the application or the Fibre Channel HPA or the hypervisor or some other kind of intelligent entity can decide which flows to put on a high priority VL, which goes to a normal VL, or which goes to a low priority virtual lane. So there is no this potential to reduce head of line blocking or not have head of line blocking, where you can have the flows that are talking to faster storage, the flows that need higher priorities go into a much faster lane. Now, what makes these lanes fast or slow is basically the number of credits they have per lane. More the number of credits, more you can spend. And similarly on the Fibre Channel virtual lanes front, more the number of credits, more frames you can send parallelly and concurrently. Okay. That's the concept. Now, it is not to say that these virtual lanes can only be between the server and the top of rack switch. They also can be between the storage and the switch. It's, if you are a storage vendor, think about how you can leverage virtual lanes, what problems or what issues your customers have, and how virtual lanes can potentially help. Okay. With that, here's my picture. Trucks are keeping right, nice and easy. So once again, just a quick reiteration, we're talking about Fibre Channel virtual lanes or VLs. We talked about how from in a traditional Fibre Channel, RReady kind of environment, there is a single physical kind of connection, and that physical connection has X number of credits. Anything before you, going ahead of you on that highway will slow you down if it is slow, and which is a problem. Now, the thing is that often in a victim culprit kind of scenario, typically the issues are found at the victim's side. And my apologies for the choice of words here, but it is really hard to find the culprit because the culprit does not exhibit any issues, so to speak. And that's why some of these issues regarding head of line blocking can be extremely hard to diagnose, especially on congestion scenarios. So here we are talking to you about the Marvell virtual lane technology. It is standards based, so it is this technology has existed between switches, and now we have the ability to extend it all the way to the endpoints, which is either the server side HPA or the Fibre Channel controller in the storage area. And there are a bunch of different use cases. Before we jump into those use cases, let me just kind of give you a little bit of behind the scenes on how virtual lanes work. Okay. So we already talked about, how there is a physical Fibre Channel link with X number of credits that's now divided into multiple different independent lanes, each one of them with their own credits. Now, from a naming perspective, just a little bit of word of caution here. We call it virtual lanes because kind of that's an easy way to identify it. Cisco calls a similar technology as virtual links, which kind of makes sense. And Brocade calls them virtual channels or endport virtual channels. So don't worry about the name again, now that you have heard about them. End of the day, it's pretty much the same thing from your perspective. How are virtual lanes set up? Basically, it is a negotiation mechanism between devices. So when an HPA or a storage actually logs into the switch, it asks the switch, hey, do you do virtual lanes? And if so, how many? And okay, if you do 3 virtual lanes, how many TX and RX buffer-to-buffer credits do you want to use for virtual lane? And what priorities do you want to use for individual virtual lanes? And once that is established, the HPA or any other mechanism, right, going through the HPA can actually tag individual frames to go on a specific VL. Okay, so if you have high priority information, it can be tagged with a high priority VL so that it makes it with more credits and faster to its destination. Now, here's the picture here on the right hand side, and this is kind of indicative. Don't take the exact numbers to heart, but what I show here in the picture is that there is a fiber channel HPA on the left, and there is switch here on the right hand side. They both have their credits. The HPA has 90 credits to give out, and the switch has 30 credits to give out. And when they log in and talk about having 3 virtual lanes, these credits get distributed across the 3 virtual lanes. And if you can read the numbers on the individual virtual lanes, VL1 has much larger credits than VL2, which is the low or the slow VL in this case. And that's why high priority traffic would be rightly put or should be put on VL1 to make it through much faster to its destination. And similarly, I think Girish will talk about this in much more detail. He has implemented a scenario in which there are attempts to relieve congestion on a storage target by quarantining flows into slower virtual lanes, and that's actually it's a beautiful little use case. But we'll get to that. I won't steal Girish's thunder. But so I promised to talk about a couple of different use cases, and there are 3 of these. But 3 is just an indicative, right? These are kind of 3 use cases that we are today discussing, but think of VLs as a foundational technology, or virtual lanes as a foundational technology. You no longer have a single lane between the HPA. Coming out of the HPA, you have multiple lanes. Imagine what you can do with it. Come talk to us. So I want to talk about a couple of different examples. The first one is a scenario. Imagine a scenario where there is an application that it is talking to both disk as well as NVMe based storage. Okay, and today, because it's a single lane, all those IOs are actually going on a single lane. So IOs going to actual spinning disk could slow down the IOs right behind them, going to much faster media. How do you prioritize flash traffic in a scenario? And this is not a dreamed up scenario, but if you just think about it as a database, right? Think about like an Oracle database, right? The database is doing a lot of things, right? It is doing a bunch of different queries operations, typically on high-speed storage, which is flash. It's also doing logging, checkpointing, things like that, which could go to cheaper, slower storage. And these 2 things can, slow each other down, so to speak. So the mechanism, the use case that is potentially possible here, and come and talk to us if you think this is interesting for your use cases, that there is an ability either for the HPA driver or some mechanism within the hypervisor, the application or operating system to detect the characteristics of the destination media, whether it is the type of media, whether it's performance characteristics, and then depending upon the destination media and our protocol, we could put flows or all the NVMe flows on a fast virtual lane and put all the rotating HDD flows onto a slow virtual lane, so that when the database is doing its queries, it is talking to NVMe-based storage, it gets to its destination without getting blocked by slower traffic like logging going to a rotating, spinning storage array. So one use case here, and this typically happens, if you think about not just a database, but there's a lot of other applications that could benefit from this. Use case number 2, which is a virtualized world. We all live in that, a bunch of different VMs, all sharing the same infrastructure, right? Now, VMs have different priorities. In fact, a lot of hypervisors, when you set up VMs, allow you to set up priorities for those VMs. But those priorities today, it's really hard to implement those priorities from the priority of the VM to the priority the VM gets on the storage fabric. So look at this use case, right? Let's say you have the picture here on the left-hand side. You have a bunch of different VMs, again, shown in different colors, and they all share the same infrastructure. If the HBA gets the ability to get the VM's priority along with the VM tag, and I'll talk about VM tag in a second, it has once the HBA driver or any other entity running there has the ability to to get the VM's priority, it can automatically put all the flows from the so-called, let's say, green VMs on a much higher priority virtual lane, and all the flows from the red VMs, let's say, on a much lower priority virtual lane. Now, going back and talking about VMID. So VMID is, again, a standard-based technology. It's implemented. For example, if you take the case of VMware ESX, right, there is APIs that exist and are implemented by Girish. Thank you, Girish. In which the HPA, for every single IO operation done on Fibre Channel, the HPA driver actually gets the identity of the VM or the tag of the VM that initiated that IO operation. So once you think of your application sitting in a VM that does a read or write, right? And that read or write translates to a request to the Fibre Channel driver. And when the request comes to the Fibre Channel driver, it also knows exactly which VM originated that IO. If it was possible, and it is, I'm sure, is some potentially feasible way in which, along with the VM's tag, if the HPA driver also got the VM's priority, low, medium, high, simple T-shirt sizes, what we could do? We could prioritize that VM and the application running on it onto 3 different virtual lanes, again, 3 simple T-shirt sizes, and translate a VM's priority into a storage fabric priority. And beautiful little use case here. Like, once again, I say, you're interested, come talk to us. Okay. And then this is another use case, which is around target side congestion. And Girish will go into kind of much more detail on this. I'm just going to kind of introduce this. So first of all, this is a use case that we have actually implemented on our Fibre Channel HPAs. And they work currently work with Cisco MDS switches. And basically, the scenario here is that imagine there is read and write traffic going from a server to a storage, and let's say the storage is not fast enough, and the media within the storage array is not fast enough. So all these writes coming into the target, they don't get synced to media fast enough, causing congestion. Right? The HPA or the server is doing writes, while the target just can't sync all of those writes to its slow media, and that caused all the congestion to build up and the congestion to spread. Now, that's a bad thing. So there are solutions around it. Basically, what happens is that the Fibre Channel switches have a mechanism, and it's called fabric notifications. Again, Girish will jump into that a little bit, where they inform the HPA that, hey, this target is congested, and then the HPA can actually move the flows that are causing the issue with this target to a slower VL, or isolate that traffic. That relieves congestion, that relieves the workload that is being put on this storage array, and helps to elevate the congestion. And it's a beautiful little use cases. We have implemented it. A lot of work has gone into, and some of the customers who have looked at this actually really like it on how it works. So with that, I think it's time for me to hand this over to Girish, and Girish is going to take you a little bit more detail, talk about to you some of the foundation behind virtual lanes, how he has looked into kind of the logic that he has implemented and is thinking about around virtual lanes and congestion. So over to you, Girish.
Okay, thanks, Nishant. Thanks for the great introduction to the virtual lanes. So in the next few slides, we would be getting a little more detailed view of how congestion can be handled or managed with the usage of virtual lanes. Before we do that, I think it would be right to spend a little bit of time understanding what are the foundational aspects of congestion identification and notification, and what are the various aspects that have been implemented over the years before we get into the details with the virtual lanes. Nishant, if you could move to the next slide, please. Thank you. So we'll talk about the fabric notifications, which, as the slide says, is the foundation for congestion mitigation. Now, this is a standards-based mechanism implemented in the switch vendors today, and this basically talks about how any sort of congestion-related information is identified and also communicated back to the endpoints. And there is a protocol endpoints can subscribe to that protocol, and based on that subscription, information flows from the switch to the endpoints indicating of conditions. So there are different types of notifications that the standards talk about. We talk about the link integrity, aptly called as potholes, where the link is in a state where it's not functioning 100%, but it's not completely broken. It's somewhere in between. There are drops in the frames, there are errors, and the entities that use the link on both ends are doing the recovery from such kind of errors. But it is always good to know that the link is not in a fully operational state, and that's the information that the switch actually can tell the endpoints, in this case, the HBA or the storage target, which actually subscribe to that. What can the, in this case, let's say the host can do with regards to the notifications on link integrity? It can take decisive actions as to how much that particular path should be used when there are link integrity issues reported on that, and choice of when to use that path. So those are the actions that the host can take upon receiving the notification. Now, the next set of notifications are for congestion. There are two categories in this, what we call as congestion and peer congestion. Congestion is to let an endpoint know that the endpoint is actually congested or is actually the source of congestion. And that's like telling you that, hey, you are congested, do something about it. The decisive action, if the endpoint chooses to implement, is it could look at reducing the rate of IO requests that are outstanding. Basically, it says that, hey, I had until now asked for data flow, which I really cannot sustain or manage. Now I could reduce the data flow that I am requesting from the storage target or the other end. And that's what the congestion notification is about. Then there's something called as peer congestion. So it's basically saying that you are operating in a zone where one entity is congested, and everybody else in that zone, because they are most likely communicating with that entity which is congested, have to be notified that there is a congestion, and if possible, you could do something to mitigate that congestion. And peer congestion basically is saying that the other end is congested and everybody else is notified of that. What can the receiver of this notification do? They could say, I would reduce the load or reduce the number of requests that have been outstanding to this particular storage target or to this particular endpoint, so that gives some reprieve in terms of recovering from that condition. The other alternatives could be, hey, if I have a different path to go to the same storage, not through this particular path, I could always make that switch for the time being, allowing the endpoint to recover from the condition that it is encountering. The last notification that the standards provide is a delivery notification. Think of a scenario where the congestion is so extreme that somewhere along the frames are being backed up, and eventually they might be dropped because of having been stuck in the fabric and not being delivered for a certain amount of time. Now, today, what happens is when a frame drop happens, none of the endpoints are aware of it. So the initiator of that frame thinks that it has sent the frame and waits for the other end to respond or not respond after a certain timeout. And that's when it would realize that something's wrong with this delivery of this frame, and then takes a mitigation action or a recovery action. Now, the delivery notification can shrink that window by saying that there is a problem, or there was a problem with the frame delivery, and I'm letting you know right away that the problem has happened, so that you do not really have to wait for the IO timeouts or likes of it before you can take a recovery action or a mitigation action. So delivery notifications basically tell you that something went wrong right away, and then the endpoints could go ahead and take the corresponding recovery action. So these four kinds of notifications, the fabric notifications, they're also called as FPINs, the acronym, fabric performance impact notifications. So these form the foundation for the congestion detection and congestion communication of congestion conditions in the fabric. Move on to the next slide. Yeah. So in terms of congestion mitigation, as Nishant alluded earlier in his talk, it has been a journey. I mean, the technology has evolved over a period of time, and different aspects have been added to the specifications, to the standards, to make it more robust and bring about a lot more awareness and a lot more capability to handle certain scenarios. So this slide here talks about the transition. Back in 2020, when the standards came out, Marvell's implementation was focused mostly on registering for the performance impact notifications, the FPINs, and being able to receive them from the switches as and when the switches delivered them, and communicating it back to the user saying, hey, this is a condition that the switch has reported, and being logged for some sort of a monitoring purpose, so that the administrators can look at it and say that, okay, there are these certain conditions that are existing in the fabric, take some sort of a recovery or a mitigation action, but those at that point were mostly manual actions that the user had to perform. So in 2021, we transitioned from the FPIN mechanism, which is a Fibre Channel extended link service, to supporting this in the form of hardware signals between the adapter and the switch, wherein the hardware signals can actually be delivered even if the conditions are so extreme that the FPIN link service frames themselves could be lost. So the condition signals mechanism allows you to be told that you are congested to the point that nothing from this fabric is actually flowing into you, but I still can let you know that there is a mechanism, that there is a condition at your end, and you got to do something about it. Forward into year 2022, as I talked about in the previous slide, for the link integrity, one of the most decisive action that an endpoint or the host in this case could take is to make a choice of the path over which IO is actually, or traffic is actually being sent down to the storage. And the path selection typically is in the charter of the multipathing solutions, which are traditionally part of the operating system storage stack. So around March 2022, we kind of worked with the various operating system vendors, specifically Linux and VMware, and tried to get the multipathing community engaged with handling the link integrity information that the switch or the fabric is actually posting to the host, make them aware of an FPIN mechanism, and use that information to do a better or a smarter path selection. So we went ahead and worked with the various operating system vendors and made sure that there is a smooth flow of this information from the fabric to the HBA, and from the HBA into the operating system multipathing stack, and then the multipathing stack could make judgments on which path to use at a given point in time based on the kind of errors that are being reported. Fast forward to that, once the link integrity portion was kind of handled, we also looked at how the hosts could themselves take some sort of actions to mitigate the congestion condition. And that's where the IO throttling technology was built in. What we did was to look at the various IO flows into the storage target and into the adapter itself, the HBA itself, and try to play around with the amount of data that's being requested, see whether the congestion is a long-term congestion or a short-term intermittent congestion, understand and identify various mechanisms by which we could mitigate those by controlling the amount of data requested or the data being sent to the storage target, depending on which entity is congested. This year, we've worked very closely with Cisco MDS team and moved to the current topic that we are talking about around the virtual lanes. We've implemented the virtual lane scheme with Cisco MDS, and this is where it is not just the notification being received at the host end, trying to mitigate the condition, but we are also trying to utilize the ability of having separate lanes for various categories of traffic. And the idea here is we wanted to move the traffic that's going to a slower device onto its own lane, so that you do not really affect any of the other traffic flows, and then also have all of this contained in one lane and automatically introduce some sort of a throttling there to help with the target coping up with this kind of a condition. So as I said, going forward, we'll continue to expand on this, try and identify more use cases. Again, we definitely would love to hear from you if you have other scenarios where you think virtual lanes or any of the FPIN technology itself could help you out with some of the conditions or some of the scenarios that are actually causing concerns in your data centers, in your environments. We would definitely like to hear that from you as well. And again, going forward, we definitely want to expand on some of these technologies to see how we could collectively put these technologies to use to address the problem of congestion, address the problem of being able to talk to different kinds of devices, some of which could be faster, some of them not so fast as well. Next slide, Nishant. Right. So from that background, I'll be jumping into the scenario where we handle the congestion. Let's take the case where the target is congested, and as Nishant alluded to in his last slide, most likely targets get congested when they are overwhelmed with traffic that is arriving at the airport, and most likely the right traffic. And the targets has got a backend stack, and the stack has to handle all of these incoming data packets and be able to respond to those on time. When that does not happen, either it could be because of a limitation in terms of the resources on the target end, or the target is oversubscribed, meaning it was configured to be in a way that it's talking to multiple initiators, and at a given point in time, all of these initiators could be deciding to dump a lot of data traffic onto the target. In either of these cases, the target can get congested. And with the FPIN mechanism, the beauty of that is the switch over a period of time monitors the resources that are associated with the given target, tries to understand how these resources are being consumed over a period of time. Eventually, it gets to a point where it detects that this target is congested, goes back and notifies the initiators in the zone that, hey, you do have a peer who's congested. And that's where the FPIN peer congestion that we talked about comes into the host. And what the HPA or the initiator in this case does is, if it is aware of virtual lanes, if it has enabled the usage of virtual lanes, it could technically move the traffic to this particular congested target onto a slow lane. Now, this does two things. One is, obviously, it isolates the traffic, meaning if that particular host is talking to other targets who are not congested, those traffic flows would be unaffected by the congested target traffic flow, and it's completely isolated, completely separated out. The rest of the traffic flows through smoothly. Now, as Nishant highlighted in his slides, the fundamental premise of virtual lanes is the distribution of credits. Now, having the distribution of credits being different between virtual lanes, and obviously with the slower lane having lower number of credits, the advantage that it brings is some sort of an auto throttling of traffic, because there are lesser number of credits to begin with for slower lanes. As soon as you move the traffic flow onto a slower lane, the amount of data that's hitting the congested endpoint would automatically be reduced, because you have lower credits to begin with. Now, this definitely helps in relieving scenarios where there are transient conditions, maybe due to lack of resources or credit stalls, as I mentioned. So it helps you to quickly recover from those scenarios. And the protocol also allows that the switch is continuously monitoring the condition with the port that was congested. And when the situation improves to a point where the switch declares that, hey, this particular endpoint is no longer considered to be congested, just like how everybody else was notified when it moved into that stage, everybody else in that zone is also notified that the particular congested target is no longer in that state. Now, what this allows us to do is the host can then take the actions of saying, okay, there was congestion, it was moved to a separate lane. Now it does not really make sense to keep the traffic in that lane. You could move it back to the normal lanes and give it the normal share of credits and handle it in a fashion that it was prior to the congestion condition being detected. So that's how the virtual lanes really can help in the case of a target or a remote port which is congested in this scenario. Next slide. Now, while I said virtual lanes definitely provide those two advantages of isolation and auto throttling, just wanted to also highlight that it is not a silver bullet by itself. Yes, it does provide a definite advantage in terms of the isolation and auto throttling, but there are some limitations to that by itself as well, which I wanted to highlight. Obviously, it is not a solution where the inherent IO throttling due to credits can only limit the traffic flow into the target to a certain extent. Obviously, depending on the distribution, that reduction in the flow may not be sufficient for the target to really recover from a condition where it is congested. An example that you could think of is an oversubscribed target. It has already been provisioned to have receive traffic from multiple initiators, and any amount of reduction that happens because of all of those initiators choosing to use a slower virtual lane may not still be sufficient to reduce the flow or reduce the amount of data that hits the traffic, the target port, and that still may not allow it to come out of the situation where it is congested. So even using virtual lanes, slower virtual lanes, the congestion condition may persist for longer than what is the right amount, right? It's not a transient condition from which it can recover. Now, the second behavior or observation that one could have is traffic is piling up at a target port. It is congested. The hosts may take an action to switch them to a slower virtual lane. Perfectly fine. The traffic congestion goes down because now obviously the amount of data flow is reduced. At some point, the switch decides that, hey, this particular target port is not congested anymore. Let everybody else in the zone know that it's not congested. The initiators could then say that everything is looking back good. Let's move the traffic back to a normal lane. And then you're back to the same situation, which was the earlier reason for having declared a condition. So meaning the traffic again goes back to the normal levels, and the switch again can detect that this is congested, and the cycle can go on back and forth. From a user's perspective, what could happen is instead of a certain level of smoothness in terms of the throughput to the traffic, throughput to the target, they could see back and forth changes of the lanes could trigger spikes. You could see an immediate ramp up in terms of the traffic, and then when congestion is detected, lane is switched, you see an immediate drop in terms of the traffic. Now, there's nothing wrong with that implementation. I mean, that's what you would expect in a system which has got a feedback mechanism, and based on the feedback, you take actions. But it does give you the sense that the traffic is not flowing very smoothly. You would have spikes and you would have trucks in your data flow. So, as I said, virtual lanes definitely provide an advantage, but by themselves, they cannot really solve all the problems that we talked about congestion. So, what is the scenario where we could really benefit from? Talk about it in the next slide. So, as I talked about, there are mechanisms where we said the host can implement some sort of an IO throttling. Now, in our assessment and in our experience, the best advantage is to couple the virtual lane concept with some of these mechanisms that the host can implement, wherein it would be able to also perform some sort of an intelligent throttling. And how would that help? BL could be the first line of defense. You first of all isolate the traffic to a slow lane, making sure that nobody else is affected. And once in that slow lane, continue to monitor if the congestion is really relieved or not relieved. And if it is not, take the next steps of trying to throttle down the traffic from the host side by reducing the number of outstanding requests to that particular target port. What this achieves is you're not only isolating the traffic and sticking with the throttling that happens with the lower number of credits, but you are also manually looking at how to reduce that flow further to really avoid congestion at the target end. And that's on the host side. Now, the other mechanisms that one could think of is you could notify the multipathing solutions that this path is now congested to a point where the multipathing can do some sort of a smart load balancing policy and not use the congested path as often as it would have otherwise used, and look at some of the parameters in terms of the number of outstanding requests, the average service time for that particular path, and then make a decision of where to place the next request going to that particular target. So in our experience and in our assessment, we feel that combining the technologies put in by the virtual lanes along with some of the mitigation strategies that could be implemented at the host, which has a more higher view of how traffic is flowing to a given device through various paths, we believe that we would be able to achieve a lot more control over how to mitigate the congestion conditions, and definitely reduce the impact to the end user application that's actually running on one of these HBAs or going through one of these HBAs to the storage targets. Okay. All right. So I think that brings me to a summary and the next steps. Definitely, we'll do a quick recap of what we have looked at. Next slide, please. So as we talked about, virtual lane definitely avoids delays, condition issues, and lack of workload-aware storage fabric can cause delays. And definitely virtual lane helps us in segregating traffic even before a scenario of condition happens, and even when the scenarios of condition happen, you could isolate the traffic that's actually causing that condition. They also enable physical layer partitioning to associate different priority for different kinds of workloads, even keeping condition as a separate topic. If you just simply want to segregate traffic based on the priority, virtual lanes definitely provide an advantage or a advantage there. And as I said, we are continuously looking inwards to see what other use cases we could utilize the virtual lanes in seeking feedback from folks here in the call, trying to see if there are specific scenarios that you would want us to see if virtual lanes help there. Welcome such ideas and questions back to us, and definitely we can work together on trying to identify where we could extend the benefit of using the virtual lanes. I think with that, I'll hand it back over to Nishant. Nishant, any closing thoughts?
Hey, thank you, Girish. I know that between you and me, at the time we have spent kind of talking to our partners and customers, there is tremendous excitement around virtual lanes. Imagine living next to a country road that was one lane, and suddenly you get a 3-lane highway there. So definitely the residents are excited. The residents include me and Girish and our customers. Like Girish said, this is a foundational technology. There's so much that can be done. Congestion is one use case. But the whole purpose that we are here at SDC talking to you storage developers, because you know your customers, you know your apps, you know your boxes. So please come talk to us, Nishant, Lodha, and Girish Basur at Marvell, and we'll love to chat further on this. With that, have a great rest of the show, and enjoy virtual lanes. Bye-bye.
Thank you, folks.